Scientists at CERN just measured something inside the world's biggest machine, and the number they got puts the universe on a countdown. Every atom around you, the air, your hands, the ground beneath you, all of it is held together by an invisible field running through all of space. And that field may be unstable. We are going to go inside the physics, meet the bubble that ends everything, and find out if the clock is already ticking. If this kind of deep science keeps you up at night, subscribe. You are going to want to see what comes next. Prepare yourself. We begin. The machine is buried 300 feet underground, running in a circle 17 miles wide beneath the border of France and Switzerland. Inside it, scientists fire particles at each other at speeds just a hair below the speed of light. The collisions are so violent that, for a fraction of a second, they recreate conditions from the first moments after the Big Bang. Most of the time, these experiments confirm what physicists already expected. But in the years following the discovery of the Higgs boson, a team of researchers ran the numbers on something that had been quietly worrying physicists for decades. They were checking the stability of the universe itself, and the answer they got was not reassuring. Here is what they actually found. The Higgs boson, the particle CERN famously detected, has a specific mass. That mass sits in a range that physicists call metastable. That word sounds technical, but the idea is simple. Picture a ball sitting in a shallow bowl on top of a hill. The ball is resting. It looks stable, but one small push and it rolls over the edge and falls all the way down. The universe, according to these measurements, is that ball. It is resting in a state that feels permanent but is sitting on the edge of something catastrophic. The team published their results, and the physics world paid attention because the implications were enormous. To understand why, you need to know what the Higgs field actually is, and that is where things get strange. The Higgs field is not a particle, it is a field, like a temperature that fills all of space. Every single point in the universe has a Higgs field value, and that value determines how particles behave. It gives electrons their mass. It shapes how atoms form. Without it, matter as we know it could not exist. Protons would fall apart. Atoms would never hold together. You would not be here. The field has been sitting at its current value since a tiny fraction of a second after the Big Bang. For almost 14 billion years, it has been perfectly stable, and that stability is the only reason the universe looks the way it does. But CERN's measurements suggest the field is not sitting at its lowest possible energy level. It is sitting at a level that is stable enough to last a very long time, maybe much longer than the current age of the universe. But stable is not the same as permanent, and that difference is the most important gap in all of physics right now. Think of it like a glass of water balanced on the edge of a table. It has been sitting there for 14 billion years without falling. Every second it stays up, you assume it is fine, but at any moment, for any reason, it could tip. And when it does, there is no catching it. The CERN team's calculation was not a casual observation. It required the most precise measurement of the Higgs boson mass ever recorded at the time. The number they landed on sits inside a narrow zone. Slightly higher and the universe would be completely stable, locked in permanently. Slightly lower and it would have already collapsed long ago. Instead, it sits right in the middle of that zone, right on the edge. Physicists gave this state a name. They called it a metastable false vacuum. And that phrase, false vacuum, describes something far stranger than it sounds. Because if the universe is sitting in a false vacuum, then somewhere out in the cosmos, the rules of physics could be completely different. And the boundary between those two realities is already moving. What that boundary actually is, and what happens when it reaches something, is where this story gets terrifying. Every atom in your body is swimming through something right now. You cannot feel it. You cannot see it. Scientists spent decades arguing about whether it even existed, but it is there, filling every cubic inch of space from here to the edge of the observable universe. It is called the Higgs field, and without it, You would dissolve in less than a second. Here is the simplest way to picture it. Imagine the entire universe is filled with an invisible ocean. Every particle that exists moves through this ocean constantly. Some particles are like pebbles dragging through thick syrup, slowed down by the field around them. Those particles pick up mass. Others are like needles slipping through water almost frictionlessly. Those particles stay light. The electron, which holds your atoms together, gets its mass from how strongly it interacts with this field. Change the field, and you change the electron. Change the electron, and atoms stop working. And if atoms stop working, everything stops. This is why physicists were so desperate to confirm the Higgs field existed. Without it, their entire picture of reality had a hole the size of the universe in it. For decades, the Higgs field was a prediction sitting inside equations. The math said it had to be there, but nobody had ever caught direct proof. Then, in 2012, CERN fired up the Large Hadron Collider and smashed protons together hard enough to knock a ripple through the Higgs field itself. That ripple appeared as a particle, the Higgs boson. For a fraction of a second, a tiny chunk of the field itself became visible. Cameras caught it, computers recorded it, scientists confirmed it. The discovery was one of the biggest moments in the history of physics. It filled the last major gap in what physicists call the Standard Model, the complete rulebook for how particles behave. But then came the problem. Once scientists knew the Higgs boson existed, they could measure its mass with precision. And the mass they measured told them something about the energy level of the Higgs field. Every field in physics has an energy level, like water sitting at different heights. The Higgs field's energy level determines how stable it is. And when physicists plugged the Higgs boson's measured mass into their equations, the answer pointed to a field that was resting, but not locked in place. It pointed to a field that could, under the right conditions, shift to a lower energy level. Shifting to a lower energy level sounds calm, like water finding a lower shelf, but a shift in the Higgs field would mean the field's value changes everywhere, instantly spreading outward at the speed of light, and every atom in that spreading zone would experience a completely different set of physics. Electrons would behave differently. Atoms would not hold together the way they do now. The chemistry that makes stars burn, the biology that makes cells work, all of it would stop. And here is the part that should make your stomach drop. The field does not need a dramatic event to shift. It does not need a supernova or a collision or anything obvious. At the quantum level, fields can tunnel through energy barriers spontaneously. The shift can start from nothing, from a single point in empty space. Physicists call that starting point a bubble, and the bubble, once it forms, follows rules that make it impossible to stop, detect, or survive. The question physicists have been quietly wrestling with is not whether the field can shift. Their own equations say it can. The question is when, and the answer depends on something so small it barely exists. Picture a ball sitting in a bowl. The ball rolls around a little, but always comes back to the center. It is stable. That is a true vacuum, the lowest possible energy state, perfectly locked, permanently safe. Now picture a different situation. The ball is sitting in a small dip on the slope of a much larger hill. It looks stable, it stays put. But if you nudge it hard enough, or if the ground beneath it shifts even slightly, the ball rolls out of that small dip and falls all the way down the hill to a much lower point. That lower point is the true vacuum. And the small dip where the ball was resting, that is the false vacuum. Physicists believe the universe is the ball in the second picture. Right now, the Higgs field is sitting in a state that appears perfectly stable. It has been sitting there for almost 14 billion years. Nothing has disturbed it. Life evolved. Galaxies formed. Stars burned and died and new ones were born. All of that happened because the Higgs field held steady. But according to calculations built on the measured mass of the Higgs boson, the field is resting in a local minimum, a comfortable dip. The actual lowest energy state of the field is somewhere lower. And if the field ever reaches that lower state, everything changes. The energy difference between the false vacuum and the true vacuum is what physicists call a potential barrier. Think of it as the wall of the bowl surrounding that comfortable dip. As long as the ball stays inside the bowl, everything is fine. But quantum mechanics adds a twist that makes this terrifying. At the smallest scales of reality, particles do not have to climb over barriers to get through them. They can tunnel through. This is called quantum tunneling, and it is a real, measured, confirmed part of physics. Electrons do it constantly. Radioactive atoms decay because of it. It is one of the strangest features of the quantum world, and it means that energy barriers are never truly walls. They are just obstacles that take time to cross. For the Higgs field, quantum tunneling means the field does not need a massive event to shift. It can shift spontaneously, somewhere in the universe, with no warning. A tiny patch of space could tunnel through the energy barrier and drop to the true vacuum. That patch would then begin to expand outward, spreading the new energy state like a ripple moving at the speed of light in every direction. That expanding region is the vacuum decay bubble. And here is the part that catches physicists off guard when they first run the numbers. The bubble does not grow slowly. Once it forms, it expands at the maximum speed the universe allows, the speed of light, and it never slows down. The laws of physics inside the bubble are permanently different from the laws of physics outside, and there is no mechanism in known science that could stop it. The universe has been sitting in this false vacuum long enough for stars to form, for planets to cool, for life to appear, for one species on one small planet to build machines powerful enough to figure this out. And the uncomfortable answer those machines are pointing to is that this calm, stable-looking universe may be sitting in a trap that has been set since the beginning. The trap has a trigger. That trigger is invisible, and something in the cosmos may have already pulled it. Somewhere in the universe, in a region of empty space with nothing nearby, a tiny patch of the Higgs field shifts. It happens with no explosion, no dramatic event, no collision or shockwave. The patch is smaller than a proton, the tiny particle sitting at the center of every atom. At that scale, quantum mechanics runs the show. And at that scale, the rules of ordinary physics stop applying. Quantum mechanics says that particles do not have fixed, certain states at every moment. They exist in a blur of possibilities until something pins them down. Fields behave the same way. The Higgs field vibrates constantly at the quantum level, never perfectly still, always flickering between possible energy states. Most of the time, those fluctuations are tiny, and the field snaps back to the false vacuum. But sometimes, by pure chance, a fluctuation is large enough to push a tiny region of the field through the energy barrier. And when that happens, the field drops to its true vacuum state in that spot. That spot is the seed of the bubble. Once the seed forms, expansion is automatic. The true vacuum state is more stable than the false vacuum surrounding it. Energy flows outward from the boundary of the bubble into the false vacuum region just outside. That boundary region then collapses into the true vacuum as well. Then the next layer, then the next. The bubble grows, and growing is all it will ever do. The expansion speed is the speed of light, 300 million meters per second, roughly 670 million miles per hour. No rocket, no signal, no force in physics can outrun it, and the bubble carries no signature that travels ahead of it. No gravity wave, no radiation, no disturbance of any kind moves faster than the bubble wall itself. Whatever is in the bubble's path has no warning. One moment, normal physics. The next, a completely different set of rules, replacing everything that existed. For the bubble to form in the first place, the fluctuation has to be just right. Too small, and the field snaps back. Too large in the wrong direction, and nothing changes. But in a universe 14 billion years old, filled with an almost uncountable number of quantum events happening every second across trillions of galaxies, the odds of that exact fluctuation occurring somewhere are no longer comfortably small. The calculation physicists use to estimate how long before such a fluctuation happens involves the size of the potential barrier between the false and true vacuum, the mass of the Higgs boson, and several other particle physics constants. When they plug in the numbers, the result is a timescale that is genuinely enormous, hundreds of billions, or even trillions, of years, much longer than the universe has existed. So, the average time before the bubble forms is far beyond anything we experience as soon. But here is the thing: average time is not the same as guaranteed safe time. The bubble could form tomorrow. The probability is incredibly small, but it is above zero. And it is above zero right now. And it was above zero yesterday. And it will be above zero every single day from now until the universe ends. Physicists do not lose sleep over the immediate risk. The numbers say we almost certainly have an enormous amount of time left, but almost certainly and definitely are very different things in quantum mechanics. The bubble might already exist, formed quietly, somewhere billions of light years away, already racing toward us at the speed of light. And if it is, nothing in the universe can send us word. Imagine a sphere. It starts smaller than a single atom, then it expands. In 1 second, it grows to a sphere about 186,000 miles wide. In 8 minutes, it passes the distance from Earth to the Sunday. In 4 years, it reaches the nearest star. In 100,000 years, it crosses our entire galaxy. And in all that time, it never slows down. The physics inside that sphere are completely unlike anything we know. Every rule that allows atoms to form, stars to burn, or cells to function is gone, replaced by something else entirely. This is the vacuum decay bubble, and it is the universe's most efficient destruction machine. To understand what makes the bubble different from every other catastrophe in physics, you have to understand what it actually changes. Most disasters destroy things. A supernova burns, a black hole crushes, a gamma ray burst radiates lethal energy across thousands of light years. But all of those events happen inside the laws of physics as we know them. The atoms involved are still atoms. The electrons still behave like electrons. The destruction is violent, but the rules are intact. The bubble destroys the rules. Inside the bubble, the Higgs field has settled to its true vacuum state, a lower energy level than the false vacuum we live in now. At that lower level, the Higgs field has a different value. That different value changes how particles get their mass. Electrons behave differently. The forces that hold atomic nuclei together shift. The chemistry that makes molecules possible changes completely. Everything built from atoms, which is everything we can see, touch, or measure, either stops working or transforms into something unrecognizable. Scientists describe the interior of a vacuum decay bubble as a region of different physics. The same particles exist, but the rules governing them are so different that nothing familiar survives. Stars would not form. Atoms as we know them might not hold together. Life, by any definition tied to chemistry, would be impossible. The bubble wall is the boundary between the two regions, and the wall is where the transformation happens. At the wall, the energy difference between the false vacuum outside and the true vacuum inside drives a violent transition. The particles crossing the wall are hit by an enormous energy change in an unimaginably short time. The result is essentially instant dissolution. There is no slow fade, no gradual change. The wall arrives, and the moment it does, the matter it meets ceases to function in any recognizable way. The terrifying elegance of the bubble is that it requires nothing to keep expanding. It does not run out of energy. It does not slow down. It does not stop at the edge of a solar system or a galaxy. It expands forever, at the speed of light, converting false vacuum into true vacuum as it goes. The universe is big enough that the bubble could travel for hundreds of billions of years and still have room to keep growing. From the outside, the bubble is invisible. It emits no light. It sends no signal ahead of itself. The space just outside the wall looks exactly like normal space until the wall arrives. One moment, everything is fine. The next moment, that moment is over. The only question that remains is whether the bubble has already formed somewhere out there, and the answer depends on a number that CERN measured very carefully. That number is the mass of the Higgs boson, and where it lands changes everything. You are standing outside on a clear night, looking up at the stars. Everything looks normal. The sky is quiet. The universe is calm. And somewhere, racing toward you at the speed of light, is the end of everything. You will never see it coming. You will never feel it approach. You will not have time to think a single thought before it arrives. The bubble wall moves at the maximum speed physics allows, and nothing in the universe can outpace it to deliver a warning. This is one of the most unsettling features of vacuum decay. Every other cosmic threat humanity has imagined comes with at least a theoretical possibility of detection. A massive asteroid shows up on radar years before impact. A nearby star going supernova sends out light and radiation that arrives before the dangerous particles do. Even a black hole gives you time to notice it is pulling everything in. The vacuum decay bubble gives you nothing. The reason is fundamental to how information travels in the universe. Every signal, every message, every form of detection we know of travels at or below the speed of light. Gravity waves travel at the speed of light. Electromagnetic radiation, which includes light, radio waves, and X-rays, travels at the speed of light. Even the theoretical fastest signal we could ever send would travel at the speed of light. The bubble wall also travels at the speed of light. This means the bubble wall and any signal it could theoretically send both arrive at exactly the same moment. There is no gap, no lead time, no fraction of a second where a detector could ping and give us a heads up. The warning and the event are the same thing, and they happen simultaneously. For something a billion light years away, this means the bubble could have formed a billion years ago and we would have no way of knowing. The light from that region is still traveling toward us, still showing us what that region looked like before the collapse. Our telescopes are showing us the past, and the bubble is already somewhere between that past image and us. Astronomers have a word for this. They call it the light cone. Everything inside your light cone, meaning everything that has had enough time for light to travel from it to you, is information you can receive. Everything outside your light cone is information you cannot receive yet. The bubble's formation event is outside our light cone. We have no access to it. We cannot know it happened. One thing that makes this even stranger is the scale involved. The observable universe is roughly 93 billion light-years across. Vast regions of it are so far away that their light takes billions of years to reach us. A bubble forming at the far edge of what we can observe would have been traveling for billions of years before we could even detect the light from where it started. By the time we see the region go dark, the bubble could already be billions of light-years closer. Physicists who run these scenarios say the math is clean and brutal. If the bubble forms anywhere within a certain radius around us, a radius defined by the age of the universe and the speed of light, we are already in the path, and we have zero chance of knowing. The comfort, if there is any, is that the bubble is overwhelmingly likely to form incredibly far away and incredibly far in the future. The odds on any given day are vanishingly small, but vanishingly small is a different thing from zero, and the universe has a lot of days left. What the bubble actually does when it arrives is something even stranger than the silence before it. The bubble wall arrives, and in less time than it takes light to cross a single atom, everything changes. The matter in its path does not explode, it does not burn, it does not get crushed or ripped apart the way it would near a black hole. Something stranger happens. The rules that hold matter together simply stop applying. And without those rules, matter cannot function. Here is why. Every atom in your body is built from smaller pieces held in place by invisible forces. The nucleus at the center, made of protons and neutrons, is held together by what physicists call the strong force. Electrons orbit the nucleus because of the electromagnetic force. These forces have the strengths they do because of the Higgs field's current value. Change the value of the Higgs field, and you change the strength and behavior of those forces. Inside the bubble, the Higgs field sits at its true vacuum value. That value is different enough from our current false vacuum value that the particles we know would behave in completely foreign ways. Electrons, which currently orbit nuclei at specific distances and energies, would have different masses. Different masses mean different orbital sizes. Different orbital sizes mean the chemistry that allows molecules to form simply does not work the same way. The bonds that hold water molecules together, that hold proteins folded into the right shapes, that allow your cells to function, those bonds depend on precise electron behavior, and that behavior depends entirely on the Higgs field. The result is that atoms, as we know them, stop being the atoms we know. They do not explode outward. They do not collapse inward. They transform into configurations that follow a different set of rules. Whether those configurations form stable structures, and what those structures would look like, is genuinely unknown. The physics inside the bubble is a different physics. Scientists cannot model it with current tools because our tools are built on the rules of the false vacuum. What we can say is that the structures we call matter, the rocks, the air, the stars, the oceans, anything built from atoms working the way atoms currently work, would cease to function in the way they do now. The transformation would happen at the speed of light. A human body hit by the bubble wall would experience zero duration of pain, awareness, or transition. The change happens faster than nerve signals can travel, faster than a single chemical reaction can complete. There is a word physicists sometimes use for this process. They call it dissolution. The organized structures of matter dissolve into whatever the new physics allows. The elements do not vanish. The particles do not disappear. They are reorganized according to a different set of rules. Rules built on a lower energy state that the universe has never shown us. Earth itself would dissolve in this way. The rock, the iron core, the oceans, the atmosphere, the thin layer of organized chemistry we call the biosphere, all of it would transform at the speed the bubble wall crosses it. Earth is roughly 8,000 miles in diameter. The bubble wall crosses that distance in less than 100th of a second. The sun would follow moments later, the entire solar system, gone in under 9 minutes, but the bubble keeps moving. And every star, every galaxy, every structure in its path meets the same fate. And the piece that makes physicists most uncomfortable is that this transformation may have already begun somewhere, because the bubble does not need anything unusual to form. It just needs time, and the universe has had a great deal of that. In 2012, a team at CERN did something that took almost 50 years and billions of dollars to pull off. They caught the Higgs boson. The particle had been predicted in the 1960s by a physicist named Peter Higgs and several colleagues working independently around the same time. The theory said the particle had to exist if the Higgs field was real. But the particle was extraordinarily hard to find because it appears for only a tiny fraction of a second before decaying into other particles. Catching it required collisions so powerful that the machines to create them took decades to design and build. When CERN finally detected it, the discovery filled the last major gap in the standard model. Physicists celebrated, and then, fairly quickly, they started getting nervous. The nervousness came from the mass. The Higgs boson's mass determines the energy level of the Higgs field, and the energy level of the Higgs field determines whether the universe is stable, unstable, or sitting in between. Physicists had been waiting for this measurement for decades, knowing that wherever the mass landed, it would tell them something fundamental about the fate of everything. The mass they measured sits right in a zone physicists had quietly dreaded. Too high, and the universe would be completely stable, locked into its current state forever. Too low, and the universe would be unstable, meaning it should have already collapsed. The measurement they got sits in the middle zone, the zone of metastability, the false vacuum zone. To make the picture clearer, imagine a chart with 3 regions. On the left, marked unstable, the universe would have already ended. On the right, marked stable, the universe will last forever in its current form. In the middle is a narrow strip labeled metastable. The measured Higgs boson mass lands in that strip, and the strip is narrow enough that the uncertainty in the measurement matters enormously. The measurement is incredibly precise, but physics at this scale involves overlapping calculations from multiple constants: the top quark mass, the strong force coupling constant, and the precise value of the Higgs boson mass itself. Each of these carries a small margin of error. When physicists combine all the margins, the universe's position on that chart shifts slightly. It could be right in the middle of the metastable zone, or it could be nudging toward the stable side. The data cannot yet tell them which. What physicists can say with confidence is that the measurement rules out a completely stable universe. The numbers do not land there. The universe is either metastable, meaning the false vacuum, or in a narrow region where the physics becomes genuinely difficult to calculate. Either way, the comfortable answer, the one where everything is permanently fine, is off the table. This is why the measurement mattered so much beyond the initial celebration. Finding the Higgs boson was the victory. Learning its mass was the revelation, and the revelation pointed toward a universe living on borrowed time. CERN has since refined the measurement multiple times. Each refinement has kept the mass in roughly the same place, sitting in the metastable zone, sitting in the false vacuum. And with every refined measurement, physicists have grown more confident that the ball is on the hilltop and the hilltop is real. Whether the ball stays up long enough to matter to us depends on something happening at the tiniest scale imaginable. Nobody sat down and picked a date. The calculation does not work like a countdown on a clock. It works like calculating the average time before a coin lands heads. You can calculate the average without knowing when any specific flip will happen. Physicists applied the same logic to the universe, and the answer they got was a number so large it barely fits in the human brain. The calculation starts with the Higgs boson mass. That mass feeds into equations describing the shape of the Higgs field's energy landscape, meaning how steep the barrier is between the false vacuum and the true vacuum. A steeper barrier means it takes longer for quantum tunneling to punch through. A shallower barrier means the flip can happen sooner. With the measured Higgs boson mass, the barrier is steep, enormously steep. The tunneling probability per unit of space, per unit of time, is so small that physicists write it as a number with hundreds of zeros after the decimal point. If you covered the entire observable universe with detectors and ran them for 1 billion years, the probability of detecting even one spontaneous vacuum decay event in that time would still be effectively zero. So when physicists say the universe has a death date, they do not mean it is happening soon by any human measure. They mean the process is probabilistic, and given enough time, the probability of at least one decay event happening somewhere in the universe approaches certainty. The timescale they calculate, hundreds of billions to trillions of years, is so far beyond the current age of the universe that it might feel meaningless. The universe is roughly 14 billion years old. The decay timescale is thousands of times longer than that. In that time, every star in the universe will have burned out. Black holes will have begun to evaporate. The universe will be cold, dark, and nearly empty long before vacuum decay becomes a statistically likely event. But here is what makes physicists uneasy. The calculation assumes we know all the relevant constants precisely, and we do not. The top quark mass, which feeds into the same equations, is known but not perfectly. If the true value of the top quark mass is slightly different from current measurements, the slope of the energy barrier shifts, and a shift in that slope could change the timeline by enormous amounts in either direction. A slightly different top quark mass could push the universe toward the stable side of the chart, or it could push it toward a shorter decay timescale. The calculation also assumes that vacuum decay can only begin through spontaneous quantum tunneling in empty space. But there are other possible triggers: high-energy events, rare cosmic conditions, things the equations might not fully capture. And there is one specific trigger that physicists spent years debating, one that humans themselves might be capable of causing. The answer was not what most people expected. Nothing caused it. That is the hardest part for most people to accept about quantum tunneling. In everyday life, things happen because other things cause them. A ball rolls because someone kicked it. A fire starts because something sparked. But in the quantum world, events can happen with no cause at all. A particle simply appears on the other side of a barrier. It did not have enough energy to cross. The barrier did not disappear. The particle did not go around it. It tunneled through, as if the barrier was not fully real. This is one of the most tested and confirmed features of quantum mechanics. Tunneling is not a theoretical curiosity. It is the engine behind radioactive decay. When an unstable atomic nucleus spits out a particle, it does so through tunneling. The particle inside the nucleus does not have enough energy to escape in the classical sense. It tunnels out. This happens billions of times per second in naturally occurring radioactive materials all around us. It happens in the electronics inside every computer chip. It is a fundamental feature of how the universe operates at small scales. And it means the Higgs field's energy barrier is not a solid wall. It is a probabilistic obstacle that quantum fluctuations can cross without any trigger. To picture this, imagine the false vacuum as a valley surrounded by tall walls. Classical physics says you need to climb the wall to get out. Quantum mechanics says you have a small chance of just appearing on the other side without climbing anything. The chance is tiny for any specific point in space at any specific moment. But the universe contains an almost incomprehensible number of points in space, and it has been running for almost 14 billion years. The probability of tunneling happening at any single point in space during any given second is so small that you could not write it as a decimal without running out of space on the page. But multiply that probability by the number of points in the observable universe, and then multiply again by the number of seconds the universe has existed, and you get a number that is still very small, but no longer zero. Every second that passes, every point in space across the universe, is another roll of a dice weighted enormously against tunneling. But the game never stops. The dice never stop rolling, and across the full timescale physicists calculate for the universe's decay. The dice eventually land on the outcome. What makes this different from every other kind of risk humanity has ever thought about is that there is nothing to fix, no way to reduce the probability, no shield, no intervention. Quantum tunneling is a feature of reality itself. You cannot turn it off. The Higgs field is tunneling somewhere on some tiny probabilistic scale right now. Every moment it stays in the false vacuum is a moment it did not happen. And that is the closest thing to good news in this entire topic. The even stranger part is that tunneling is not the only way the collapse could start. There are conditions in the universe so extreme that the laws governing tunneling might not even apply in the usual way. Conditions that exist inside some of the most violent objects in the cosmos. And scientists found one that should have set off vacuum decay long ago, if it was going to happen at all. The universe just had its 14 billionth birthday. That sounds like a long time, and by human standards, it is an almost incomprehensible span. But in the context of vacuum decay, the age of the universe is not a source of comfort, it is a source of concern. Here is why. Every second the universe exists, it is rolling the dice on vacuum decay. Every single point in space, across every galaxy, every star system, every stretch of empty void between galaxies, each one of those points represents another opportunity for the Higgs field to tunnel. The probability at any single point during any single second is vanishingly small, but the universe is enormous, and it has been rolling those dice for 14 billion years. That means the universe has already run through an enormous number of opportunities for the decay to start. The fact that it has not started yet, as far as we can tell, is actually meaningful information. Physicists call this the survival probability. If the universe has survived 14 billion years without the decay triggering, that tells us something about the minimum height of the energy barrier. The barrier must be at least high enough to survive that many rolls of the dice. And the measured Higgs boson mass is consistent with a barrier that high. So the age of the universe and the measurement from CERN actually line up. They both point to the same conclusion. The barrier is real, it is high, and the decay is not imminent. But survival probability cuts both ways. Every additional billion years the universe ages adds another enormous batch of dice rolls to the total count. The universe at 14 billion years old has had 14 billion years of chances. At 100 billion years old, it will have had 100 billion years of chances. The longer it runs, the higher the cumulative probability of the decay occurring somewhere. Think of it like a very long, slow lottery. Each ticket has an almost impossibly small chance of winning. But if you buy enough tickets over enough time, eventually someone wins. The universe is buying tickets every second, at every point in space, forever. The longer it runs, the closer the cumulative ticket count gets to the winning number. There is also a subtler issue that physicists consider. The universe is expanding. As it expands, the volume of space increases. More volume means more points in space. More points in space means more dice rolls per second. As the universe grows, the rate of new opportunities for vacuum decay does not stay constant. It grows with the expansion. This does not dramatically change the timescale. The total timescale for decay is still enormous compared to the current age of the universe. But it means the decay risk is not a flat line. It slowly increases over cosmic time. For now, the universe is young enough that the cumulative probability remains very low. But the age that matters is not 14 billion years. The age that matters is the total lifespan of the universe, however long that turns out to be. And on that scale, the decay is not an unlikely freak accident. It is a built-in feature of how the universe eventually ends. The unsettling thought is not that the decay is close. The unsettling thought is that it might already be happening in the part of the universe we cannot see yet, triggered by conditions we have never observed. And those conditions might already exist in places much closer to home than the edge of the observable universe. Right now, as you listen to this, there may be a bubble of different physics somewhere in the universe, already moving toward us at the speed of light. We would have no way of knowing. The bubble carries no signal ahead of it. It emits no light we can detect. Every telescope on Earth points at the past, not the present. The images we see of distant galaxies show us what those galaxies look like millions or billions of years ago, because light takes time to travel. If a bubble formed in a galaxy 2 billion light years away 2 billion years ago, the light showing us that galaxy still arriving today is showing us what the galaxy looked like before the collapse. The collapse itself has had 2 billion years to travel toward us. Physicists have actually thought carefully about this scenario. They calculate what they call the expected number of bubble nucleation events that might have occurred within the observable universe over its entire history. Given the Higgs boson mass and the height of the energy barrier, that number is extraordinarily small, much less than one in the entire history and volume of the observable universe, which means it is overwhelmingly likely that no bubble has formed anywhere near us, or anywhere in the region of space we can observe. But the observable universe is not the whole universe. The universe extends far beyond what we can see. Light from the most distant regions has not had time to reach us yet. Physicists estimate the full universe could be vastly larger than the observable portion, potentially hundreds or thousands of times larger, maybe more. In that larger volume, the probability of at least one bubble nucleation event having occurred somewhere is significantly higher than in the observable portion alone. If a bubble formed in the unobservable universe, far beyond the edge of what our telescopes can ever reach, It could be racing toward us right now at the speed of light, and we would never know until the moment it arrived. This might sound like an abstract threat, too distant and too uncertain to matter, but the structure of the argument is important. The probability is not zero. The bubble is allowed by the physics. The universe is large enough that somewhere the dice may have already been rolled and won, and the consequences of that, if true, arrive without warning. Astronomers do have one indirect check. If the bubble had formed inside the observable universe at some point in the past, it would have converted that region of space to a different physics. That region would look different to our telescopes. We would see dark patches, regions where the normal signatures of stars, galaxies, and cosmic background radiation simply stop or change character. So far, detailed surveys of the cosmic background radiation, the faint afterglow of the Big Bang that covers the entire sky, show no signs of such a bubble impact. The sky is clean. The universe, as far as we can see, shows no evidence of a decay event. That is genuinely good news. But the sky being clean only tells us what happened within the range our instruments can measure. The universe beyond that edge remains a place we cannot check. And then there is an entirely separate question, one that kept physicists up at night for years before they worked through the calculation. What if humans had the power to trigger the collapse themselves? Physics rarely produces clean agreement. For every paper arguing the universe sits in a dangerous false vacuum, another team runs the numbers slightly differently and lands somewhere else. The disagreement is not about whether the Higgs field exists or whether vacuum decay is theoretically possible. Those points are settled. The argument is about exactly where on the stability chart the universe sits, and that question hinges on measurements that are extraordinarily difficult to pin down. The measurement everyone focuses on is the top quark mass. The top quark is the heaviest of all the fundamental particles. It interacts with the Higgs field more strongly than any other particle. That strong interaction means the top quark's mass has an outsized effect on the energy landscape of the Higgs field. Shift the top quark mass slightly, and the entire stability picture shifts with it. Physicists have measured the top quark mass many times. The measurements cluster around a specific range, but the margins of error are significant compared to where the stability boundary sits. And the stability boundary, the line between the metastable false vacuum and the stable true vacuum, runs right through the range of measurement uncertainty. The universe's fate sits inside the error bars. A team of physicists in Europe ran a detailed analysis using the best available measurements and concluded the universe most likely sits in the metastable zone, the false vacuum. Their calculation put the central value comfortably in the metastable region. A separate group reanalyzed the same data with slightly different assumptions about how to handle higher-order corrections in the equations, and found a result nudging toward the boundary between metastable and stable. A third group focused on uncertainties in the strong force coupling constant and found that even small shifts there could push the universe firmly into the stable zone. None of these groups made errors. They were all doing careful, peer-reviewed physics. The disagreement comes from the genuine difficulty of the calculation and the genuine limitations of current measurements. What almost no group finds is complete stability. The measurements consistently rule out the comfortable conclusion. Even the most optimistic analyses tend to place the universe inside, or very close, to the metastable zone. The debate is about how deep inside the false vacuum we sit, how far from the stable side of the line, and how long the survival timescale actually is. The answer to that question will improve as accelerators get more powerful and measurements get more precise. CERN has been refining the top quark mass measurement over multiple experimental runs. Future colliders being planned by several countries would produce far more precise measurements of both the top quark mass and the Higgs boson mass, potentially resolving the current uncertainty. Until those measurements arrive, physicists are working with their best current data, which places the universe in a situation that is uncomfortable but enormously unlikely to resolve itself within any time frame relevant to human history. The minority view, the one that argues for a stable universe, is a minority for a reason. The data leans against it, but the data is not yet sharp enough to rule it out entirely. And that ambiguity sits at the heart of one of the strangest questions in cosmology. What does the universe's connection to dark energy tell us about the vacuum? Because dark energy and the Higgs field may be far more connected than most people realize. The universe is speeding up. That was the discovery that blindsided astronomers in 1998. Galaxies are not just moving away from each other, which was already known. They are accelerating. Something is pushing them apart, faster and faster over time. Physicists gave this something a name: dark energy. And despite decades of research, nobody knows what it actually is. Dark energy makes up roughly 68% of everything in the universe. Ordinary matter, the stuff you can see, touch, and measure, makes up less than 5%. Dark matter, invisible but detectable through its gravitational effects, makes up about 27%. Dark energy is the dominant ingredient of the cosmos, and physicists cannot tell you what it fundamentally is. One of the leading ideas connects dark energy directly to the vacuum of space. Empty space, according to quantum mechanics, is not actually empty. It seethes with virtual particles constantly popping in and out of existence. This seething has energy, called vacuum energy, and that energy could be what is driving the accelerating expansion of the universe. Here is where the Higgs field enters the picture. The energy of the vacuum is linked to the energy level of the Higgs field. Right now, the Higgs field sits in the false vacuum. The energy associated with that state contributes to the overall energy density of the universe. If the Higgs field were to drop to the true vacuum, the energy density of the vacuum would change, and a change in vacuum energy density would affect the expansion rate of the universe. Physicists have run calculations on what vacuum decay would do to the expansion of the universe, and the results are dramatic. A lower vacuum energy state could dramatically alter how space expands. In some scenarios, the true vacuum might actually have a negative energy density compared to our current state. Negative vacuum energy, combined with the expansion already in progress, could produce effects that are currently beyond our models to fully describe. The connection runs deeper than just expansion rates. The value of dark energy, which astronomers measure as an extremely small positive number, is one of the most precisely balanced quantities in physics. If it were slightly larger, the universe would expand so fast that galaxies could never form. If it were slightly smaller or negative, the universe would collapse back on itself. The fact that dark energy has the tiny positive value it does is itself a puzzle, and that puzzle connects to why the Higgs field sits where it does on the energy landscape. Some physicists argue that the current value of dark energy and the current state of the Higgs field are connected through the same underlying physics, a deeper layer of reality that our current theories do not fully describe. If they are right, then understanding vacuum stability and understanding dark energy are two faces of the same problem, and right now scientists understand neither one completely. What they do understand is that the Higgs field was not always sitting in the false vacuum. In the first moments after the Big Bang, it was in a completely different state, and what happened to it then, and why it ended up where it is now, is a story that reshapes everything about how we think about the universe's beginning. 14 billion years ago, the universe was a furnace. In the first fraction of a second after the Big Bang, the temperature of the universe was so extreme that no structures could form. Protons and neutrons did not exist yet. Atoms were completely impossible. The energy density was so high that even the fundamental forces of physics behaved differently than they do today. And the Higgs field, the same field sitting quietly in the false vacuum right now, was in a completely different state. At those temperatures, the Higgs field was effectively zero. Particles moved through it without gaining mass. Electrons, quarks, and all the other fundamental particles zipped around at nearly the speed of light, massless, moving in all directions through a universe of pure, violent energy. The rules we know today, where particles have specific masses and atoms hold together in predictable ways, did not apply. As the universe expanded, it cooled. And as it cooled, the Higgs field underwent a phase transition. This is the same kind of process that happens when water cools into ice. Water flows freely. Ice locks into a crystal structure. The molecules did not change, but their arrangement and behavior changed completely because the temperature dropped below a critical point. The Higgs field went through its own critical temperature. At a specific point in the cooling of the early universe, the field shifted from its zero state into the state we know now. Particles that were massless suddenly gained mass. The rules of chemistry and atomic structure switched on. The universe went from a sea of massless particles racing around at light speed to a place where mass existed and structures could form. This transition happened extremely fast. In cosmological terms, it was essentially instantaneous, and it set the initial conditions for everything that followed. The precise value the Higgs field settled into during this transition determined the masses of every particle, the strengths of the forces, and ultimately the structure of the universe we live in. Here is the crucial question physicists ask about that transition. Why did the field settle where it did? The false vacuum sits at a specific energy level. The true vacuum sits lower. During the phase transition in the early universe, the field had to choose an energy state. It chose the false vacuum. Why? One answer is temperature. During the phase transition, the universe was still hot enough that thermal effects kept the field in the higher energy state. As the temperature dropped, the field became trapped there, like a ball settling into a bowl on a hillside when there is still too much thermal energy for it to roll all the way down to the valley. Another answer involves processes that happened even earlier in the universe's history during a period called inflation. Inflation stretched the universe from a microscopic speck to an enormous size in an incredibly short time. The conditions during inflation may have set the initial configuration of the Higgs field in ways that physicists are still working out. What both answers have in common is that the Higgs field's current state, the false vacuum we live in, was not inevitable. It was a result of specific conditions during the universe's earliest moments. And those conditions mean we are living in a state that, while stable for an enormous amount of time, is not the final resting place of the universe's energy. The universe is heading toward the true vacuum eventually. The only question is when, and what happens if something in our own cosmic neighborhood accelerates that process. When CERN announced plans to collide particles at higher and higher energies, a small but vocal group of people raised an alarm. If the Higgs field is in a metastable false vacuum, and if it can be destabilized by a high-energy event, then smashing particles together at record energies seems like exactly the kind of thing you would want to avoid. The concern made headlines. Critics asked whether the scientists running the world's most powerful particle accelerator had done their homework, whether they had checked the math. They had, and the answer they found was both reassuring and revealing. The argument against CERN causing vacuum decay comes down to a simple comparison. The Large Hadron Collider, the most powerful particle accelerator ever built, can collide protons at a combined energy of around 14 tera-electron volts. That sounds enormous. By any human engineering standard, it is. But compared to what happens naturally in the universe, it is a whisper. Every single day, cosmic rays slam into Earth's atmosphere at energies millions of times higher than anything the Large Hadron Collider can produce. Cosmic rays are charged particles, mostly protons, accelerated by supernova explosions, black holes, and other violent astrophysical events to speeds so close to the speed of light that their energy dwarfs anything a human-built machine can achieve. These collisions have been happening in Earth's atmosphere for as long as Earth has existed, about 4.5 billion years. Earth is still here. But the argument goes further than Earth. Cosmic rays with energies far beyond what CERN can generate also slam into neutron stars. Neutron stars are the densest objects in the universe outside of black holes. A neutron star packs a mass greater than our Sun into a sphere roughly 12 miles across. The density at the center is so extreme that matter behaves in ways that push the limits of known physics. Cosmic ray collisions on neutron star surfaces involve conditions more extreme than anything CERN could theoretically produce, even with machines thousands of times more powerful. Neutron stars throughout the galaxy have been absorbing cosmic ray impacts for billions of years, trillions of collisions at energies astronomically beyond human capability. And neutron stars have not triggered vacuum decay. Physicists wrote this argument up formally, and it is one of the most solid safety analyses in particle physics. The conclusion is clear. If particle collisions at any realistic energy could trigger vacuum decay, the universe would have triggered it already, long before humans appeared. The cosmic ray argument makes CERN concerns about vacuum decay essentially moot. The mechanism that could actually trigger vacuum decay is quantum tunneling, which operates completely independently of energy input. You cannot trigger it deliberately any more than you can make a radioactive atom decay on command. It happens on its own schedule, determined by quantum probability, not by anything colliders do. The good news is that CERN cannot end the world through the Higgs field. The bad news is that the thing that could end the world through the Higgs field is something entirely beyond human control or detection. But before physicists fully relaxed about particle colliders, someone asked a follow-up question about neutron stars, one that pointed towards something unexpected. A neutron star is an object that should not be able to exist by common sense. Take a star roughly 8 to 20 times more massive than our Sunday. Now, collapse it into a sphere about 12 miles across, roughly the distance you would drive to reach the next town over. Every cubic inch of that sphere contains more mass than a mountain. The gravity on the surface is 200 billion times stronger than what you feel standing on Earth. If you somehow stood on the surface of a neutron star, you would be crushed to a thickness thinner than an atom in less time than it takes to think about it. Inside a neutron star, matter has been squeezed past the point where individual atoms can exist. Electrons get pushed into protons, converting them into neutrons. The whole star becomes essentially one enormous atomic nucleus, packed to a density that tears apart every chemical bond, every atomic structure, and most of the physical rules that govern ordinary matter. The pressure at the center of a neutron star reaches conditions that no laboratory on Earth can come close to replicating. And onto this extreme environment, the universe pelts cosmic rays constantly. Cosmic rays hitting a neutron star surface do not just slam into rock the way they slam into Earth's atmosphere. They hit matter already compressed to its absolute physical limit. The collision energies at a neutron star surface, when you account for the intense gravitational field accelerating incoming particles even further, reach values that make the Large Hadron Collider look like a toy compared to a nuclear weapon. These collisions have been happening across billions of neutron stars scattered throughout the Milky Way for billions of years. The total number of extreme energy collisions that have occurred on neutron star surfaces across the observable universe is a number so large that writing it out would fill several books. And yet, neutron stars still exist. The universe still runs on the same physics it always has. The Higgs field has not been destabilized. Physicists take this as one of the strongest arguments that the false vacuum is more stable than a naive reading of the numbers might suggest. The universe has been running natural experiments at energies no human machine will ever approach for billions of years. And those experiments have consistently produced the same result: no decay. But neutron stars also revealed something else, something that shifted how physicists think about the most extreme environments in the universe and what they might do to the Higgs field. Because neutron stars are extreme, but they are not the most extreme thing in the universe. There is a class of objects where the conditions become so severe that the calculations physicists use for neutron stars break down entirely. Objects where matter does not just compress, it disappears. And what happens to the Higgs field at the edge of those objects is a question that does not yet have a clean answer. A black hole does not crush matter, it removes it from the universe entirely. At the center of a black hole sits a singularity, a point where density becomes infinite and the equations of physics produce answers that make no sense. The laws governing space, time, and matter break down completely at that point. Whatever happens, there is beyond what any current theory can describe. And that breakdown is exactly why black holes became one of the most debated objects in discussions about vacuum stability. The concern runs like this. If conditions extreme enough to destabilize the Higgs field exist anywhere in the universe, the singularity at the center of a black hole seems like the most likely candidate. The energy density there is incomprehensibly high. The curvature of space-time is infinite. Every known physical quantity goes to extremes that make neutron star interiors look mild by comparison. So would the Higgs field remain in the false vacuum at a black hole's singularity, or would the conditions there be extreme enough to push it over the barrier into the true vacuum? Physicists have worked through this carefully. The answer splits into two parts, and both parts are strange. The first part involves what happens inside the event horizon, the point of no return surrounding a black hole. Once matter crosses the event horizon, it cannot send any signal back to the outside universe. Light cannot escape. Gravity waves cannot escape. If the Higgs field inside a black hole were to collapse to the true vacuum, the resulting bubble would be trapped inside the event horizon. It could not expand outward into the surrounding universe. The black hole's own gravitational structure would contain the decay. This is actually a stabilizing feature. Black holes, rather than being triggers for vacuum decay, might act as containment vessels. Any decay event inside the horizon stays inside the horizon. The second part is more unsettling. Some physicists have argued that the boundary of a black hole, the event horizon itself, could have effects on the Higgs field in the region just outside it. The intense gravitational field near the horizon distorts space-time in ways that affect quantum fields permeating that region. Whether those distortions are enough to lower the effective energy barrier for vacuum decay near black holes is an open question. The calculations are extremely difficult, requiring a combination of general relativity and quantum field theory that physicists do not yet have a complete framework to handle. What the current best analyses suggest is that black holes do not dramatically accelerate vacuum decay in their immediate surroundings. The quantum fluctuations near the horizon are intense, but the geometry of the situation, with the horizon itself acting as a kind of boundary, appears to suppress rather than enhance the probability of spontaneous decay. There is one scenario, however, that some physicists find genuinely thought-provoking. As a black hole evaporates through a process called Hawking radiation, it slowly loses mass over an enormous timescale. Near the very end of that evaporation process, when the black hole has shrunk to near the Planck scale, the smallest meaningful size in physics, the conditions become truly extreme. The final moments of black hole evaporation are a region where quantum gravity effects dominate completely, and in that region, the Higgs field behavior is genuinely unknown. The universe contains black holes of all sizes, from those a few times the mass of the Sun to monsters billions of times more massive. Some of the smallest, if they exist, may have already evaporated. What happened to the Higgs field in their final moments is a question that sits at the frontier of physics, and the answer, if anyone ever finds it, might tell us something profound about whether the universe can survive its own most extreme creations. Imagine stepping through a door. On this side of the door, the universe works the way you have always known it. Atoms hold together, stars burn, gravity pulls things toward each other at a predictable rate, chemistry happens, life is possible. On the other side of the door, every single one of those things works differently, and nobody who steps through ever comes back to tell you what they found. The inside of a vacuum decay bubble is the most alien environment imaginable. Physicists can describe what changes when the Higgs field drops to the true vacuum. They can calculate how particle masses shift, how the forces change, how the energy landscape of reality itself transforms. What they cannot tell you is what the result looks like, because the true vacuum state of the Higgs field is a place no observer from our physics could survive to observe. Start with electrons. In our current universe, the electron has a specific mass, determined by its interaction with the Higgs field at the false vacuum level. That mass determines the size of electron orbitals around atomic nuclei. Those orbital sizes determine how atoms bond with each other. That bonding is the foundation of all chemistry. Every molecule, every protein, every cell, every organism that has ever lived is built on electron orbital chemistry. In the true vacuum, the Higgs field has a different value. The electron's mass changes, the orbitals change, the bonding rules change. Whether stable atoms can even form in the true vacuum is genuinely uncertain. The specific value of the true vacuum is unknown because we have never measured it. We only know the false vacuum value we live in. The true vacuum sits somewhere below, at a lower energy level. But exactly how far below is one of the things current physics cannot pin down. Some calculations suggest the true vacuum could support a universe with completely different particle physics, different particle masses, different force strengths, potentially even a different number of stable atomic configurations. Whether any form of complexity, stars, planets, chemistry, anything we would recognize as structure, could exist in that universe is unknown. Other calculations suggest the true vacuum might support almost nothing, a universe of maximum entropy from the start, too uniform and low energy for any structures to condense from, a universe of spreading sameness, with no gradients of energy to drive the formation of stars or the chemistry of life. The troubling part is that from inside the bubble, if any kind of observer could exist there, the physics would feel perfectly normal. Their atoms, their forces, their entire reality would operate by the true vacuum rules. They would have no way of knowing their universe was different from ours, just as we have no way of knowing our universe is sitting in a false vacuum rather than a true one. This raises a question that some physicists take seriously. If a vacuum decay bubble produces a region with different physics that can still support structure, could that region eventually give rise to its own stars, planets, and life? Could the bubble be, from the inside, a new beginning rather than an ending? The answer depends on physics we cannot yet calculate. The true vacuum is a place our current equations cannot fully describe from the outside. What we do know is that the boundary between our universe and that unknown region is moving, and if it ever reaches us, the transformation is total. Every structure built on our version of physics ends simultaneously, at the moment the wall arrives, and the speed of that wall means there is no version of this where some of us survive and some do not. The bubble wall crosses Earth in less time than a nerve signal can travel. The universe might already be full of them, scattered across the cosmos, invisible to every telescope we have ever built. There may be regions where the physics is completely different from what we know, places where the Higgs field already collapsed to the true vacuum long ago, where atoms behave by different rules, where the stars, if any form at all, burn by a different set of equations. This idea flows directly from the physics of vacuum decay. If the false vacuum can collapse anywhere in space at any time, and if the universe is large enough and old enough, then some regions may have already undergone the transition. The bubble that formed in those regions expanded at the speed of light in all directions. If the bubble formed far enough away from us, its outer edge has not yet reached our location. But between that bubble and us, everything is still running on false vacuum physics. From our perspective, those regions look like ordinary space. The light we receive from a galaxy that will later be swallowed by a bubble still looks normal because the light left before the bubble arrived. We are watching the galaxy's past, not its present. Physicists call these hypothetical regions vacuum decay domains. Each one is defined by when and where the original bubble nucleation event occurred. The domain expands at the speed of light in every direction from its origin point. Any matter caught inside has already undergone the transition to true vacuum physics. The idea of multiple domains with different physics sounds similar to the concept of a multiverse, and the two ideas do overlap, but there is a crucial difference. The multiverse, as often described, involves completely separate universes that never interact, each existing in its own space and time. Vacuum decay domains exist inside our universe, within our space-time. They are separated by bubble walls rather than by separate space-times. If two vacuum decay domains ever expanded into each other, their walls would collide. What happens at a collision between two bubble walls is a question at the frontier of theoretical physics. Some models suggest the collision would produce an intense release of energy along the collision surface. Others suggest the two domains would simply merge if they both decayed to the same true vacuum state. If they decayed to different states, assuming multiple true vacuum levels are possible, the collision would produce a boundary between two incompatible physics regimes, a wall within a wall. Whether any of this is actually happening somewhere in the universe right now is impossible to say with certainty. The evidence either way is inaccessible. The regions beyond the edge of the observable universe, where the first bubble nucleations might have occurred, are permanently outside our information horizon. But the physics allows it, and the physics is what drives the next question. A question that connects vacuum decay to something much bigger than the end of our universe. Something that might explain where our universe came from in the first place. What if our universe is someone else's vacuum decay? The idea sounds like something from a science fiction film, but it follows from real physics in a way that a growing number of cosmologists take seriously. To understand it, you need to think about energy landscapes not just for our universe, but for a deeper layer of reality beneath it. String theory and related frameworks suggest that the laws of physics we experience are not the only possible set of laws. There may be an enormous number of possible configurations of the fundamental constants, particle masses, and force strengths, each one corresponding to a different vacuum state. This collection of possible universes is sometimes called the string theory landscape, and the landscape may contain states at many different energy levels. If a universe exists at a higher energy level, a false vacuum relative to some lower state, it can undergo vacuum decay. The bubble forms. The region inside drops to the lower energy state, and inside that lower energy state, with its different particle masses and force constants, a new set of physics applies. From inside the bubble, that lower energy state is the entire universe. The bubble expands forever, filling a region of space-time with its new physics. If those physics are complex enough, stars might eventually form, planets might condense, chemistry might happen. Life, following whatever rules the new physics allows, might arise, and that life would look up at its sky and wonder how the universe began. Our universe began with the Big Bang. The Big Bang created a state of extraordinary energy and density that expanded and cooled into the cosmos we know. Some physicists have proposed that the Big Bang itself was the interior of a vacuum decay bubble that nucleated in a higher energy parent universe. Our entire observable universe, every galaxy, every star, every atom, exists inside the bubble that formed when a region of that parent universe dropped to a lower vacuum state. If this picture is correct, our universe is a child bubble, and our own vacuum decay, when it eventually occurs, will be the birth of a child bubble inside our universe. A chain of nested universes, each one born from the decay of its parent. The chain could go upward and downward indefinitely. Parent universes birthing child universes through vacuum decay, each child universe carrying slightly different physics determined by the energy level it dropped to. The multiverse, in this picture, is not a collection of separate creations. It is a family tree written in the language of energy levels. This framework, sometimes called bubble nucleation cosmology, is speculative. There is no direct experimental evidence for parent universes or for the string theory landscape that would contain multiple vacuum states. But the math is consistent, and the idea has attracted serious attention because it addresses one of the deepest puzzles in physics. Why do the constants of our universe have the values they do? Why is the electron mass exactly what it is? Why does gravity have its particular strength? If our universe is one bubble among many, each with different constants determined by which vacuum state it landed in, then the answer becomes statistical. We observe the constants we do because those are the constants of the bubble we happen to exist in. The constants are not designed, they are inherited from a parent universe we will never see and cannot measure. And the universe our own decay creates will inherit a new set of constants from us. The word sounds almost gentle, metastable, like something that is mostly stable, almost fine, a little bit fragile, but basically okay. In reality, metastable describes one of the most extreme situations in physics, a state that can persist for an enormous amount of time while remaining fundamentally impermanent. A state where the only thing standing between the current order and total transformation is a probabilistic barrier that quantum mechanics can tunnel through. Physicists use the term precisely. A metastable state is one where a system rests at a local energy minimum, the bottom of a bowl, but the bowl sits above a deeper minimum somewhere else in the energy landscape. The system is stable against small disturbances. It bounces back from nudges. It can persist for a very long time, but it is not at the globally lowest energy level, and quantum mechanics says that given enough time, it will eventually find its way to that lower level. The universe in the false vacuum is metastable. The Higgs field sits at its current value, stable against any disturbance of ordinary size, but resting above the true vacuum. The energy barrier between the two states is high enough that the timescale for spontaneous tunneling is vastly longer than the current age of the universe. But the barrier has a finite height, and quantum mechanics does not respect finite barriers forever. Most of mainstream physics accepts the metastable interpretation. The measured Higgs boson mass, combined with the measured top quark mass, and the best available calculations of the energy landscape, points consistently toward a false vacuum. The calculations have been checked and rechecked. Independent groups using different methods reach similar conclusions. The universe is almost certainly metastable. The word almost is doing enormous work in that sentence. What metastable does not mean is imminent danger. The timescale for decay is so enormous that no human, no civilization, no species that will ever evolve on Earth will live to experience it through natural vacuum decay. The stars will burn out first. The black holes will evaporate first. The universe will enter a cold, dark, nearly featureless state long before the probability of vacuum decay becomes significant on human timescales. But metastable also does not mean safe in any absolute sense. The probability of decay is never zero. The dice roll every second, at every point in space. The timescale is enormous, but not infinite. And the mechanism by which the decay occurs, quantum tunneling, is fundamentally unpredictable at the level of any individual event. The metastable universe is the universe that makes sense of the CERN measurements. It is the universe that explains why the Higgs boson mass landed where it did. It is the universe that connects particle physics to cosmology in a single, sobering picture. And it is the universe that means every cosmological model, every long-term prediction about the future, every vision of what the cosmos will look like in 100 trillion years carries a footnote. A quiet reminder that the foundation of physics is not locked in place permanently. It is resting, waiting, sitting in a bowl on a hillside. The bowl has been holding for 14 billion years. The probability says it will hold for trillions more. But the bowl is not the valley, and the valley exists. What humanity does with that knowledge, and whether future science can sharpen the picture enough to know exactly how far from the valley we sit, is a question with more riding on it than any other question in physics. In 1983, a philosopher and physicist named Brandon Carter proposed an idea so uncomfortable that some of his colleagues wished he had kept it to himself. The argument is built on probability and a single assumption: that you are a random observer among all the observers that will ever exist. If you accept that assumption, it leads to a conclusion that is genuinely disturbing. Here is the logic. Imagine a lottery where the total number of tickets is unknown. You draw your ticket and it has the number 50,000 on it. You now have information about the total number of tickets. If the total were 10 billion, your ticket being number 50,000 would mean you were drawn extremely early, in the first tiny fraction of all possible draws. That would be extraordinarily unlikely for a random draw. If the total were 100,000, your number is right near the end, which is what you would expect for a random draw from that pool. The argument says you should bet on the interpretation that makes your position less surprising. If you are a random observer, you should expect to find yourself somewhere in the middle of all observers, not at the very beginning or the very end. Apply this to humanity. Roughly 100 billion humans have ever lived. You are one of them. If humanity goes on to produce trillions of people over the next millions of years, then being one of the first 100 billion would make you extraordinarily early, a vanishingly unlikely position for a random observer. The doomsday argument says this is evidence against humanity having an enormous future population. It suggests the total number of humans who will ever live is probably not much larger than the number who have already lived, which suggests humanity does not have an enormous future ahead of it. Philosophers and scientists have argued about this for decades. Some reject the underlying assumption, pointing out that treating yourself as a random observer across all of history requires assumptions about probability that may not be valid. Others take the argument seriously as a probabilistic signal, even if not as a certainty. The connection to vacuum decay is indirect but meaningful. The doomsday argument does not specify a mechanism. It does not say vacuum decay is what ends humanity. It simply says, statistically, intelligent observers should not expect to exist near the very beginning of their species' history. And by most estimates of what humanity could become, we are near the very beginning. The argument is not physics. It is philosophy of probability applied to population, but it rhymes with the physics of vacuum decay in a way that some find impossible to ignore. Both point toward the same quiet conclusion. The long-term future of intelligent life in this universe may be shorter than our optimism suggests. What the doomsday argument cannot tell you is the mechanism, the timeline, or whether it applies at the level of humanity, specifically, or intelligent life in the universe, more broadly. For those answers, you need physics, and the physics gives you numbers. Very large numbers. But large numbers have a way of feeling less comforting once you understand what sits on the other side of them. The number physicists calculate for the decay timescale of the universe is so large that our normal sense of time completely breaks down trying to hold it. The current best estimates place the expected lifetime of the false vacuum somewhere between 1 followed by hundreds of zeros years, on the shorter end of the uncertainty range, to numbers so astronomically larger that they defy any meaningful comparison to human experience. The uncertainty in the calculation is itself enormous, stretching across many orders of magnitude depending on the precise values of the top quark mass and other constants. To put even the shorter end of that range in context, consider what the universe will look like before the decay becomes statistically significant. In about 5 billion years, the sun will exhaust its hydrogen fuel and expand into a red giant, engulfing the inner planets. In about 100 trillion years, the last stars in the universe will burn out, leaving only black holes and cold stellar remnants drifting through an increasingly dark cosmos. In roughly 10 followed by 67 zeros years, even the protons making up ordinary matter may decay, if proton decay happens at the rate some theories predict. In 10 followed by 100 zeros years, black holes of stellar mass will have fully evaporated through Hawking radiation. All of that happens before the false vacuum decay becomes a statistically expected event, assuming the current best estimates are correct. The universe will have gone cold, dark, and effectively dead by any recognizable measure long before the Higgs field collapses. Vacuum decay. If the decay timescale sits at the longer end of current estimates, would be the final event in a universe already stripped of everything we would call interesting. So why does the timeline matter? If the decay happens so far in the future that it follows the death of every star and the evaporation of every black hole, why should anyone care? The answer is that the timeline is not guaranteed. It is a probabilistic average. The decay can happen earlier than the average, just as a coin can land heads on the first flip, even if the average number of flips to get heads is 10. The dice that determine when the decay happens are weighted enormously toward the far future, but they could, by chance, come up early. The other reason the timeline matters is that it depends critically on measurements that are still being refined. If the top quark mass turns out to sit at a value slightly different from current measurements, the height of the energy barrier changes. A lower barrier means a shorter decay timescale. The uncertainty in the current measurements is large enough that the true timescale could be significantly shorter than the central estimate, or significantly longer. Future measurements at higher precision colliders could sharpen the picture dramatically. A more precise top quark mass measurement would nail down the energy barrier height, narrowing the range of possible timescales and telling physicists, with much better confidence, how long the universe has in its current form. That measurement is coming, and the number it produces will be one of the most important numbers in the history of science. There is a theory that would make the universe permanently safe. If it is true, the Higgs field sits in a true vacuum, not a false one. The stability problem disappears. Vacuum decay becomes impossible. The universe, by the rules of this theory, is locked into its current state forever. The theory is called supersymmetry, and CERN has been looking for it for years. So far, it has found nothing. Supersymmetry proposes that every particle we know has a partner particle called a superpartner with different properties. The electron has a partner called the selectron. The quark has partners called squarks. The photon has a partner called the photino. These partner particles have never been detected, but the theory predicts they must exist at some energy scale. And if they do, they dramatically change the stability calculations for the Higgs field. The reason supersymmetry matters for vacuum stability comes from how quantum fields interact with each other. In the current standard model, the Higgs field receives quantum corrections from all the other fields in physics. These corrections affect the energy landscape of the Higgs field, shifting the heights of the barriers and changing where the local and global minima sit. In the standard model, without supersymmetry, those corrections push the Higgs field toward the metastable false vacuum interpretation that the measurements support. Supersymmetric partner particles would contribute their own quantum corrections, and those corrections would partially cancel out the ones from ordinary particles. The cancellation is not accidental. Supersymmetry is structured so that the partner particles' corrections precisely balance the ordinary particles' corrections in a mathematically elegant way. The result is a Higgs field that sits in a true vacuum, genuinely stable, with no metastability and no decay timeline. CERN specifically built the Large Hadron Collider, capable of energies where supersymmetric partners were predicted to appear, based on the most popular versions of the theory. It ran those experiments. It found nothing. No selectrons, no squarks, no photinos. The absence of a discovery is itself a discovery. It rules out the simplest versions of supersymmetry, the ones most theorists had been hoping for. This is why CERN's failure to find supersymmetry alarmed the physics community. Finding it would have solved multiple problems at once, including vacuum stability, the nature of dark matter, and several other puzzles in the standard model. Not finding it in the predicted energy range means either supersymmetry does not exist, or it exists, but at much higher energies than predicted, energies that may require machines far more powerful than the Large Hadron Collider to reach. Some physicists have moved away from supersymmetry entirely, looking for other extensions of the standard model that might stabilize the Higgs field. Others argue that supersymmetry is still viable at higher energies and that a future, more powerful collider could find it. Until one of those scenarios plays out, the metastable false vacuum remains the best interpretation of what CERN has actually measured. The universe, by current evidence, is not protected by supersymmetry. The theory that would have made everything safe has not shown up, and the machine that was supposed to find it is already planning its next upgrade. Physics history has a pattern. One measurement arrives. Everything physicists thought they understood shifts. New equations replace old ones. The map of reality gets redrawn. It happened with quantum mechanics. It happened with relativity. It happened when the expansion of the universe was discovered to be accelerating. And it will happen again. The question is, which measurement does it next? For vacuum stability, the measurement that would change everything is the top quark mass. More specifically, a top quark mass precise enough to pin down the Higgs field's energy landscape with enough clarity to resolve which side of the stability boundary the universe sits on. Right now, the top quark mass sits in a measured range that straddles the critical line between metastable and stable. The central value points toward metastability, but the error bars are wide enough that the stable interpretation cannot be ruled out. A more precise measurement that pushed the central value firmly to one side of that line would settle the question. If the precise measurement confirmed metastability with tighter certainty, it would sharpen the timescale calculation. The height of the energy barrier, currently uncertain enough to allow decay timescales across many orders of magnitude, would narrow. Physicists would have a much better sense of how long the false vacuum is likely to persist. If the precise measurement instead showed the universe sits in the stable zone, the entire framework shifts. Vacuum decay through Higgs field tunneling would be ruled out. The universe's death sentence, as currently written, would be commuted. Physicists would need to look elsewhere for what eventually ends the cosmos. Beyond the top quark mass, a discovery of any new particle interacting with the Higgs field could dramatically shift the picture. Supersymmetric particles, if found at any energy scale, would alter the quantum corrections to the Higgs potential and potentially stabilize it. A new type of scalar field, interacting with the Higgs in a specific way, could raise the effective energy barrier. Even a more precise measurement of the strong force coupling constant, which feeds into the same equations, would sharpen the calculation. The next generation of colliders being designed and proposed around the world would produce measurements of this precision. A circular electron-positron collider, producing enormous quantities of Higgs bosons in cleaner conditions than the Large Hadron Collider, would measure the Higgs boson mass and its properties with a precision orders of magnitude beyond current capabilities. A future proton-proton collider, operating at 3 times the Large Hadron Collider's energy, would directly probe the energy scales where new physics might appear. These machines are decades away from operation. Funding, international cooperation, and engineering challenges stand between current plans and actual data. But the scientific community understands what is at stake. The measurements these machines would produce do not just satisfy scientific curiosity. They answer a question about whether the universe we live in is permanent or provisional. That question has been open since 2012. The answer is sitting in the data, waiting for a machine precise enough to read it clearly. And while physicists wait for that machine, 2 competing theories about how the universe ends are going head to head. The universe has more than one scheduled ending. Physicists have identified several ways the cosmos could eventually stop being the cosmos. 2 of them stand out as the most scientifically grounded contenders. One is vacuum decay, which we have been following through this entire story. The other is something called the Big Rip, and the 2 endings are as different as any 2 things in physics could be. Vacuum decay you already understand. The Higgs field tunnels to the true vacuum. A bubble forms. It expands at the speed of light. The laws of physics inside the bubble transform completely. Matter dissolves into configurations governed by different rules. The process spreads through the universe forever. The ending is a transformation, a wholesale replacement of one set of physics with another. The Big Rip works through dark energy. Right now, dark energy is causing the universe to expand at an accelerating rate. Galaxies are moving apart faster and faster. If dark energy remains constant, the expansion accelerates, but at a manageable rate. Structures like galaxies and solar systems remain bound together by gravity, even as the spaces between them grow. The universe gets larger and emptier, but it does not tear itself apart. However, if dark energy is not constant, if it grows stronger over time, the story changes dramatically. A growing dark energy would eventually overcome not just the gravitational attraction between galaxies, but between stars within galaxies, then between planets within solar systems, then between objects on a planet's surface, then between molecules in a rock, then between atoms in a molecule, then between the protons and neutrons inside an atomic nucleus. Every bound structure in the universe would be ripped apart, from the largest galaxy cluster down to the smallest subatomic particle, in a finite amount of time. The Big Rip ends in a universe of unconnected particles, each one isolated from every other by an expansion too fast for any force to bridge. Physicists currently favor vacuum decay over the Big Rip for one reason: the data. Measurements of dark energy over time show no evidence that it is growing. Its value appears constant, or at least close to constant. If dark energy stays constant, the Big Rip does not happen. The expansion continues forever, but it never tears structures apart. Vacuum decay, driven by the Higgs field's measured metastability, remains the more physics-grounded prediction for the universe's ultimate end. The distinction matters beyond academic interest. A Big Rip universe ends in maximum disorder, maximum separation, maximum entropy. Every particle isolated forever. A vacuum decay universe ends in transformation to a different physics, one that might, in principle, allow new structures to form. One that might, in some distant theoretical sense, contain complexity again. Which version of the end is true changes the answer to the deepest question humans have ever asked. Is the universe heading toward permanent death or toward transformation? Is the end truly final, or is it a door? The physics says we are most likely heading toward transformation. But what that transformation does to time itself is something that challenges every intuition we have about what reality means. Time is not what you think it is. Most people experience time as a river. It flows forward, consistently, from moment to moment. But physicists have known for over a century that time is more complicated than that. It stretches and compresses with velocity. It bends near massive objects. It is woven together with the three dimensions of space into a single fabric called space-time. And the rules governing time depend entirely on the laws of physics in the region where time is being experienced. Inside a vacuum decay bubble, those laws change, and with them, the behavior of time changes. To understand how, you need to know that time in physics is not separate from the fields that fill space. The rate at which time passes, the way events are ordered relative to each other, and the very structure of causality, meaning what can cause what and in what sequence, are all tied to the physical laws governing the region. Change the laws, and you potentially change all of those properties of time. In our universe, the Higgs field's value sets the mass of particles. The mass of particles determines how they interact with each other over time. The interactions define what we experience as the flow of events. At the boundary between the false vacuum and the true vacuum, where the bubble wall crosses, all of these relationships change simultaneously. The transition is not gradual, it is a sharp boundary. On one side, our physics. On the other, the true vacuum physics. Some theoretical models of vacuum decay predict that at the bubble wall itself, the energy density is so extreme that space-time geometry is dramatically warped. The transition region might involve conditions where the normal separation between space and time, the mathematical framework physicists use to describe how events relate to each other, breaks down or becomes meaningless in the familiar sense. Inside the bubble, if any form of physics persists, time as a dimension still exists. But its relationship to the other dimensions might be different. The rate at which quantum processes occur, which defines the pace of causation in the universe, would be governed by the true vacuum particle masses and force strengths. Whether those processes run faster, slower, or in a completely reorganized sequence compared to our universe, depends on the specific value of the true vacuum, which we cannot currently calculate. There is a more extreme possibility that some theorists have raised. If the true vacuum energy is very different from the false vacuum energy, the effective cosmological constant inside the bubble could be strongly negative. A strongly negative cosmological constant causes space-time itself to collapse inward rather than expand outward. A universe with a strongly negative cosmological constant does not expand. It collapses catastrophically fast. Time inside that bubble, measured by any internal observer if one could exist, would be radically compressed. The entire interior of the bubble might collapse to a singularity within a cosmological instant. This would make the bubble a self-contained catastrophe, a region of space that forms, transforms, and collapses before any signal from its interior could interact with the surrounding false vacuum. Whether this extreme scenario is realistic depends on where the true vacuum energy actually sits, and that is a number physics cannot yet provide. But the fact that it remains possible means the end of our universe might not be a long, slow transformation. It might be a brief, violent collapse happening inside a bubble that our universe never fully understands. And if we could somehow detect that bubble coming, we still could not stop it. But could we even see it? Every instrument ever built by human civilization works by detecting signals. A telescope captures light. A radio receiver captures electromagnetic waves. A gravitational wave detector captures the ripples that massive objects make in space-time as they move. Every signal these instruments detect travels at the speed of light or slower. They are all limited by the same ceiling. The vacuum decay bubble travels at the speed of light. This makes detection, in any useful sense, physically impossible. The bubble does not produce a signal that races ahead of it. It does not disturb the cosmic background radiation in a way that travels faster than the wall. It does not send gravitational waves that propagate ahead of its leading edge. The wall is itself the first signal of its existence, and it arrives exactly when it does, without a moment's notice. Astronomers have considered whether there might be indirect signs. One idea involves the cosmic background radiation, the faint glow of microwave light left over from the Big Bang that fills the entire sky. If a vacuum decay bubble had formed somewhere in the observable universe and was expanding, it might produce a distinctive signature in the cosmic background radiation as it approached and then intersected with the surface from which that radiation was emitted. Some physicists proposed searching for circular cold or hot spots in the background radiation as possible signatures of bubble collisions from very early in the universe's history. Surveys of the background radiation have been conducted with extraordinary precision. The Wilkinson Microwave Anisotropy Probe and the Planck satellite mapped the cosmic background radiation across the full sky at resolutions that reveal temperature variations smaller than 100,000th of a degree. These maps show no compelling evidence of bubble collision signatures. The sky, as far as these instruments can see, is statistically consistent with a universe that has not experienced a nearby vacuum decay event. But these surveys have a fundamental limitation. They can only detect signatures from bubbles that formed and collided with observable cosmic structures within the region of space that light has had time to cross in the 14 billion years since the Big Bang. Bubbles forming outside that region, or forming recently enough that their signatures have not yet reached us, are completely invisible. A bubble forming 1 billion light-years away today would not be detectable by any instrument for 1 billion years. And by that time, the bubble wall itself would arrive long before any indirect signature reached us. Some physicists have proposed that a sufficiently advanced civilization might detect quantum fluctuations in the Higgs field that indicate increased tunneling probability in a nearby region of space. But this requires a theory of quantum gravity that does not yet exist, instruments of a precision billions of times beyond anything currently built, and a measurement timescale on which civilizations do not persist. The blunt conclusion is that detection is not a practical possibility with any technology science can envision. The bubble, if it comes, arrives as the first and last event. There is no warning system. There is no early detection network. There is no version of this threat that humanity could prepare for or respond to. The impossibility of detection connects directly to a question that has haunted astronomers for decades. A question about silence. A silence that vacuum decay might explain completely. The universe is roughly 13.8 billion years old. It contains over 2 trillion galaxies. Each galaxy holds hundreds of billions of stars. Many of those stars have planets. Some of those planets have conditions suitable for life. By raw numbers alone, the universe should be teeming with civilizations, some of them billions of years older than humanity. And yet we hear nothing. No radio signals from distant civilizations. No megastructures visible to our telescopes. No evidence of any kind that intelligence has arisen anywhere in the cosmos except here. The universe is vast and apparently empty of detectable minds. This is the Fermi paradox, named after physicist Enrico Fermi, who captured the problem in a single question at a lunch table in 1950. Where is everybody? Dozens of proposed answers exist. Perhaps life is extraordinarily rare. Perhaps civilizations destroy themselves before developing interstellar communication. Perhaps advanced civilizations choose silence. Perhaps the distances involved make contact statistically impossible even over billions of years. Each proposed solution has problems that other solutions try to patch. Vacuum decay offers one of the cleanest and most sobering explanations. If the false vacuum is metastable, and if advanced civilizations have the potential to last billions of years, then over the history of the universe, many civilizations might have reached the level of technological complexity that humanity is only beginning to approach. Some of those civilizations might have lasted long enough to encounter a vacuum decay event. A vacuum decay bubble traveling through a galaxy would leave no survivors and no warning. An entire civilization, including every record, every signal, every artifact it ever produced, would dissolve at the bubble wall. Any radio signals the civilization had been transmitting would stop abruptly at the moment the bubble arrived. Any transmissions sent before the bubble arrived might still be traveling through space, but they would be old and faint by the time they reached us, indistinguishable from background noise. More chillingly, a vacuum decay event would convert the entire region of space the civilization occupied into true vacuum physics. Every structure in that region, every star, every planet, every molecule of evidence that a civilization ever existed would transform. There would be no ruins, no artifacts drifting through space, no radio echoes, nothing. Vacuum decay is the only proposed explanation for the Fermi paradox that leaves absolutely no evidence of prior civilizations. Every other catastrophe, wars, pandemics, climate collapse, even asteroid impacts, leaves something behind. Vacuum decay leaves nothing because the medium in which evidence would be preserved, matter governed by false vacuum physics, ceases to operate as it did. This makes vacuum decay a candidate for what some physicists and philosophers call the Great Filter, a barrier in the development of life that prevents civilizations from becoming long-lasting. The filter might lie behind us, in the difficult emergence of complex life, or it might lie ahead, in a physical process that ends civilizations before they mature. Vacuum decay as a great filter does not require a high probability of decay per unit time. It only requires that the universe is old enough and large enough that some regions have already experienced it, and that the civilizations caught in those regions had no way out. The silence of the universe may be the loudest evidence we have that something is coming. The bubble wall crosses the space between atoms in less time than any clock on Earth can measure. Let us walk through what happens to Earth specifically, moment by moment. If a vacuum decay bubble ever reaches our solar system, the The sequence is so fast that the word moment barely applies. But physicists can reconstruct the sequence from first principles. The bubble approaches at the speed of light. Earth is roughly 25,000 light-years from the center of the Milky Way galaxy. The galaxy itself is 100,000 light-years across. A bubble originating outside our galaxy would travel for millions or billions of years before reaching us. A bubble originating inside the galaxy, in a region closer to Earth, would arrive sooner. In all cases, the approach is invisible. At the moment the bubble wall reaches the outer edge of our solar system, roughly 4 billion miles from the Sun, everything in its path begins to transform. The wall crosses that distance in about 6 hours. In 6 hours, from the outer edge of the solar system to the Sun, every object in the path transitions to true vacuum physics. The planets of the outer solar system, Jupiter, Saturn, Uranus, Neptune, and everything in between, transform in sequence as the wall sweeps inward. The transformations are instantaneous at each location. The wall is thin, potentially as thin as a single Planck length, the smallest meaningful distance in physics, roughly 1.6 times 10 to the negative 35th of a meter. Crossing the wall takes less time than any physical process we can measure. When the wall reaches Earth, the planet's diameter of roughly 8,000 miles is crossed in less than 0.04 of a second. Every structure on Earth, every mountain, every ocean, every city, every cell in every organism transforms as the wall passes through. The transformation propagates from one side of the planet to the other in less time than it takes sound to travel 1 inch. The Sun follows roughly 8 minutes later. The wall sweeps through a sphere 1 million miles wide in under 9 seconds. Within those 9 minutes from the moment the wall hit Earth to the moment the Sun transforms, the entire inner solar system has converted to true vacuum physics. The process continues outward into the galaxy. Billions of stars, over timescales of tens of thousands of years, each one converting as the bubble wall passes. From the perspective of any observer on Earth, in the moment before the wall arrives, there is no warning and no experience of the event. Consciousness depends on nerve signals moving through tissue at speeds of hundreds of miles per hour. The bubble wall moves at 670 million miles per hour. The wall crosses the distance. A nerve signal travels in a blink of an eye in a time frame billions of times shorter than the blink itself. There is no pain. There is no awareness. The transition happens at a scale below the resolution of any biological process. The last moment of experience for every conscious being on Earth is exactly the same as any other moment, because the last moment is indistinguishable from the moment before it. For the universe around us, the transformation continues silently. The bubble does not know we were here. Not everyone reads the physics of vacuum decay as a story of destruction. A small but thoughtful group of cosmologists looks at the same equations, the same bubble mechanics, the same transition from false vacuum to true vacuum, and sees something different. They see a process of cosmic renewal, and the reasoning is not wishful thinking. It follows from the physics. Consider what the bubble actually does. It does not annihilate matter. It transforms the rules that govern matter. The particles inside the bubble still exist. Energy is conserved. The quarks that made up protons and electrons are still there, interacting with each other according to the new rules of the true vacuum. The universe inside the bubble is not empty. It is reorganized. Whether anything complex can emerge from that reorganization depends entirely on the specific value of the true vacuum, which, as we have established, is a number physics cannot yet calculate. If the true vacuum supports a rich set of particle interactions, atoms of some kind might form, stars of some kind might condense, chemistry of some kind might occur. Given enough time, and the universe has an enormous supply of that, complexity might re-emerge. Life following new rules, built from new atomic structures, experiencing a reality whose physics is as internally consistent as ours. From inside the bubble, there is no memory of the false vacuum. The true vacuum is simply the universe. The beings inside, if they arise, have no way of knowing they live in a region that was once governed by different rules, just as we have no way of knowing, with certainty, that our universe is not itself the result of a prior vacuum decay event in a parent universe. This picture transforms vacuum decay from a death sentence into something more like a generational process. The universe does not end, it changes phase. The false vacuum produces a long era of structure, stars, planets, and potentially life. Then the true vacuum replaces it, carrying its own potential for structure and life, by whatever rules its physics allows. Some physicists connect this to the anthropic principle, the observation that the universe we live in has physical constants that permit our existence. In a multiverse generated by repeated vacuum decay events, the child universes that support complex life are the ones that get observed. Universes with physics too hostile for life exist, but produce no observers. The universe we observe is necessarily one that supports observers. If vacuum decay is generative rather than purely destructive, the universe is not heading toward an ending. It is heading toward a transformation whose output is unknown. Whether that output resembles what we know, or something completely beyond our current imagination, is a question no physics experiment can currently answer. What physics can do is keep refining the measurements that tell us where we sit in the energy landscape, how far from the true vacuum we rest, and how long the current phase of the universe can be expected to last. Those measurements are happening now, at machines built by people who understand what the numbers mean. And the most important of those machines, and the most important of those measurements, is what the story of the universe's fate ultimately comes down to. The Large Hadron Collider is currently in its third major operational run. Engineers and physicists have spent years upgrading the machine's systems, increasing its collision rate and improving its detectors. The goal of this run is to produce more precise measurements of the Higgs boson's properties than any previous run achieved. More collisions mean more data. More data means smaller statistical uncertainties. Smaller uncertainties mean the measurements sit closer to the real values of the constants physicists need. The top quark mass measurement is a central target. Every Higgs boson produced in a collision carries information about how the Higgs field behaves. Every top quark event provides another data point for pinning down the mass that sits at the heart of the vacuum stability calculation. Over years of running, the accumulated data from this run will sharpen both measurements significantly compared to what physicists had available when the original metastability calculations were performed. CERN has also approved a next-generation machine called the High Luminosity Large Hadron Collider. Luminosity, in particle physics, refers to the collision rate. More collisions per second means more data per unit time. The High Luminosity upgrade, planned to begin operations in the late 2030s, would produce 10 times more collision events per second than the current machine. The resulting datasets would reduce measurement uncertainties to levels that could genuinely resolve the question of whether the universe sits firmly in the metastable zone or closer to the stable boundary. Beyond CERN, the international physics community is studying proposals for a next-generation circular collider, a machine with a circumference of roughly 60 miles compared to the Large Hadron Collider's 17 miles. A machine of that scale, operating at energies 3 times higher than anything the current collider can reach, would produce Higgs bosons with a precision and volume that would make current measurements look rough by comparison. The top quark mass, the Higgs boson mass, and dozens of other constants that feed into the vacuum stability calculation would all be measured with dramatically reduced uncertainty. These machines would also probe energy scales where supersymmetric particles, if they exist, might finally appear. Finding even one supersymmetric partner would transform the stability picture. It would confirm the extension to the standard model that stabilizes the Higgs field. It would push the universe from the metastable zone into the stable one, and it would mean the vacuum decay story, as currently written, has a happy ending. Finding nothing, Running out of energy scales to probe and still detecting no new physics would mean the standard model holds and the metastable interpretation stands. The universe is what the current measurements say it is, resting in a false vacuum, separated from the true vacuum by a barrier high enough to last an enormous time, but not by a barrier that lasts forever. Whether humanity ever achieves the measurement, precision needed to give a definitive answer depends on whether the civilization building those measurements survives long enough to complete them. The machines needed are decades away. The funding requires international cooperation at a scale that assumes political stability across many countries over long time periods. The measurements themselves require years of data collection after the machines start running. Physics moves slowly by human standards. But on the timescale of the universe, it moves extraordinarily fast. The universe has been sitting in the false vacuum for 14 billion years, silently holding its energy above the true vacuum floor, rolling the quantum dice every second at every point in space. It has billions of years left by almost any estimate before the probability of natural decay becomes significant. Enough time for a species that learned to split the atom 70 years ago to build machines that pin down the energy landscape of reality to the precision needed for a real answer. The death date of the universe, if it has one, is written in the mass of the Higgs boson and the mass of the top quark. Physicists know where to look. The measurement is within reach of machines humanity can build. And the answer, when it arrives, will be either the most reassuring number in the history of science or the most sobering one. Either way, it will be the truth. And knowing the truth about the universe we live in, however vast and strange and indifferent that universe turns out to be, is the thing that makes us worth finding in the first place.